In June 2026, a team of researchers analyzing brand new infrared data from the James Webb Space Telescope found something that stopped them mid-sentence. Buried inside a narrow wavelength window on the surface of Pluto was an absorption signal, a specific dip in the spectrum where light was being swallowed that matched no known molecule in the entire published planetary science literature. Not a gas anyone had catalogued, not an ice anyone had confirmed, not a compound ever detected on any world or any exoplanet ever studied by any instrument humanity has ever built. And then the same exact signal, at the same wavelength, showed up again in data from Saturn's moon Titan, a completely different world nearly 1 billion miles closer to the Sun. The scientists who found it did not hedge. They stated plainly that they could not say what it is. This is not internet speculation or a clickbait rumor. This is a peer-reviewed and formally submitted finding from an international research team using the most powerful telescope ever launched into space, and it lands just 1 year after an earlier Webb discovery. Already forced planetary scientists to rewrite what they thought they understood about Pluto's atmosphere. Together, these two findings add up to something almost impossible to fully absorb. A tiny frozen world that most people wrote off decades ago as a dead, irrelevant rock at the edge of the solar system has turned out to be running an atmospheric cooling system unlike anything else known to exist, hiding an unidentified substance on its icy crust, slowly bleeding its own atmosphere onto a neighboring moon and staining that moon permanently red, possibly concealing a liquid ocean beneath a shell of frozen nitrogen, and growing fields of jagged methane ice blades taller than a 15-story building, arranged in a band that may wrap most of the way around its equator. None of this was supposed to be there, and almost none of it was visible to science until Webb finally turned its instruments toward Pluto. To understand why that matters so much, you have to go back to where the story of Pluto actually begins. Pluto was discovered in 1930 by a 24-year-old assistant named Clyde Tombaugh, working at an observatory outside Flagstaff, Arizona. His entire job was to compare photographic plates of the same patch of sky taken on different nights, hunting for a single point of light that had shifted position against the background stars. For the next 85 years, Pluto remained essentially a mystery, a faint dot too far away and too small for any Earth-based telescope to resolve into anything more than a blur. That changed in July 2015, when NASA's New Horizons spacecraft completed a 9.5-year journey across nearly 3 billion miles of space and shot past Pluto at more than 30,000 miles per hour. It had exactly one opportunity. No orbit, no second pass, just a narrow window of close approach before the spacecraft kept moving deeper into the Kuiper Belt, never to return. What it sent back rewrote nearly every assumption the field had built up over 85 years of studying a distant dot. A massive pale, heart-shaped plain of nitrogen ice stretched across a huge section of the surface, smooth and geologically young-looking, in a way that suggested something was still actively reshaping it. Mountains of solid water ice rose more than 10,000 feet high, frozen so hard at Pluto's temperatures that they behave structurally more like granite than the soft ice most people picture. Layers of blue haze rose hundreds of miles above the surface, visible when backlit by the sun, clearly structured in a way that told researchers something dynamic was happening in that impossibly thin atmosphere. And strangest of all, the dark polar regions of Pluto's largest moon, Charon, were stained a deep reddish brown that nobody could yet explain. New Horizons had answered decades of old questions and opened up roughly twice as many new ones, but it only got that single pass. Whatever it missed would stay missed unless a different kind of instrument could eventually pick up where it left off. That instrument turned out to be the James Webb Space Telescope, though not in the way most people expect. Webb is not simply a camera, at least not only that. Its real power is spectroscopy, the ability to break light apart into its individual wavelengths with extraordinary precision, reading the chemical fingerprint of whatever it observes. Pointed at a faint pinprick of reflected sunlight nearly 4 billion miles away, Webb can identify which molecules are present on a surface or inside an atmosphere, how warm different layers of that atmosphere actually are, and how those conditions shift over time, all without physically traveling anywhere near the target. Every molecule absorbs and emits light at its own specific, unique wavelength. Read those wavelengths precisely enough, and you effectively get a full chemical inventory of an entire world from clear across the solar system. The specific technical barrier Webb finally broke through with Pluto had frustrated astronomers for years. Pluto and its large moon Charon sit so close together in the sky, as seen from Earth, that earlier telescopes simply could not cleanly separate their individual heat signatures. Any measurement of Pluto's temperature would inevitably pick up stray heat from Charon sitting right beside it in the field of view, blurring the results into uselessness. Webb's much larger mirror, and its significantly more sensitive mid-infrared instrument called MIRI, which operates across wavelengths from roughly 5 to 27 micrometers, finally solved that problem for good. For the first time in the entire history of Pluto science, researchers could read Pluto's own thermal emissions separately from its companion moon, giving them a clean atmospheric diagnosis that had simply been impossible until now. The team behind this breakthrough, led by astronomer Tanguy Bertrand at the Paris Observatory, used Webb data collected in 2022 and 2023. What they found, published in the journal Nature Astronomy in June 2025, confirmed a prediction that planetary scientist Xi Zhang at the University of California, Santa Cruz had made 8 years earlier, back in 2017. Zhang's original hypothesis struck many of his own colleagues as unlikely enough that he later admitted, in his own words, that it had seemed like a crazy idea at the time. His proposal was that the haze particles suspended in Pluto's atmosphere were not trapping heat the way similar haze traps heat in the atmosphere of Saturn's moon Titan. Instead, he argued they were doing the exact opposite, absorbing sunlight during the day and then radiating that energy straight back out into space as infrared heat faster than Pluto's extremely thin atmosphere could ever hold onto it. Not a blanket, but a radiator, actively pulling heat away from a world that barely had any warmth to spare in the first place. Webb's MIRI data confirm this directly. The haze particles floating in Pluto's upper atmosphere are genuinely controlling the entire energy balance of that atmosphere, heating up and cooling down as they absorb and release radiation, and the net result is that Pluto's upper atmosphere runs somewhere around 30 degrees Fahrenheit, colder than existing computer models had predicted it should be. Bertrand described this to researchers as a genuinely new kind of climate, unlike any other atmosphere found anywhere in the solar system. On every other world scientists have studied in this kind of detail, the gases themselves do most of the work driving atmospheric climate. On Pluto, it is the solid particles suspended inside those gases that appear to be running the entire show. The team framed the discovery as both confirming Zhang's original hypothesis and opening up an entirely new line of investigation into whether similar haze-driven cooling might be happening on other cold, hazy worlds, including Neptune's large moon Triton, and whether something similar may have played out in Earth's own ancient atmosphere billions of years before oxygen ever built up in our skies and fundamentally changed the chemistry of our planet. That connection to early Earth is genuinely worth pausing on. Pluto's atmosphere is made up mostly of nitrogen, with methane, carbon monoxide, and traces of other compounds mixed in. That composition is broadly similar to what many researchers believe Earth's atmosphere looked like in its very earliest period, long before photosynthetic life transformed our planet into the oxygen-rich world that exists today. Sunlight striking those early Earth molecules would have driven some of the exact same photochemical reactions that sunlight striking Pluto's atmosphere drives right now, producing organic compounds, building up haze, and distributing chemistry through the atmosphere and down onto the surface below. Pluto, sitting in deep freeze at temperatures where chemistry moves painfully slowly but never fully stops, has effectively been running a version of that ancient pre-life atmospheric chemistry continuously for roughly 4 billion years. That makes it not just a distant curiosity, but a working real-time model of conditions that once preceded life on Earth and no longer exist here in any form we can still access. That same photochemistry produces one of Pluto's most visually striking features, the dark reddish-brown material coating large portions of its surface, concentrated especially across a broad equatorial region roughly the size of Alaska. These compounds, called tholins, form when sunlight breaks apart methane and nitrogen molecules high in the atmosphere. The resulting fragments recombine into heavier, darker organic compounds that slowly drift downward and settle onto the surface over time. Tholins belong to the same broad chemical family as some of the organic molecules researchers believe may have played a role in the chemistry that eventually led to life on early Earth. On Pluto, that same slow production of biological building blocks has been running uninterrupted for billions of years, quietly settling onto a surface too cold for any of it to ever go anywhere or react into anything more. It is, in effect, a 4 billion year snowfall of organic chemistry landing on a world where temperatures sit near 400 degrees below zero, and nothing is ever warm enough to do anything with it. Those extreme temperatures are worth sitting with for a moment because they are almost impossible to picture. Sunlight reaching Pluto is roughly 1,000 times fainter than sunlight reaching Earth. Surface temperatures there hover somewhere between about negative 387 and negative 369 degrees Fahrenheit. At those levels, nitrogen, the very gas making up roughly 78% of the air you're breathing right now, freezes completely solid and becomes part of the actual landscape. The atmospheric pressure at Pluto's surface measures only about 13 microbars, compared to Earth's roughly 1 million microbars. Even standing there in a fully protective spacesuit, the cold at those temperatures would reach through almost instantly, damaging exposed surfaces long before the total absence of breathable air ever became the immediate danger. Now, for the discovery that is still so new that researchers are actively working out what it even means. In June 2026, a team led by researcher Bruno Bazard at the Paris Observatory submitted a paper to the journal Astronomy and Astrophysics, reporting a detection described in unusually direct, almost blunt terms. While analyzing Webb infrared data from Titan and Pluto within a narrow wavelength range, a spectral window where haze absorption is low enough for the instrument to actually see straight through to the surface underneath, the researchers found an absorption feature they simply could not identify. They combed through the entire published planetary spectral literature. They found no documented molecule, no known gas, no confirmed ice compound in any prior study of any solar system body or exoplanet that produces an absorption signal at that specific wavelength. The feature showed up twice in the Titan data, captured by two separate Webb instruments operating across two different wavelength ranges, collected months apart from one another. That detail matters enormously because a signal appearing in only one instrument at one single moment could easily be dismissed as a glitch or a stray artifact. The same signal showing up independently in two separate instruments is far harder to explain away. And then the exact same feature turned up again in Pluto data collected back in May 2023 at essentially the same wavelength within the margin of measurement error. Two very different worlds, sharing one unexplained absorption signal at a wavelength that matches nothing currently in the scientific literature. Titan sits roughly 4 times closer to the Sun than Pluto, is significantly larger, and even has liquid methane lakes and rivers flowing across its surface. Pluto, by contrast, is frozen completely solid, much smaller, and sits out in the distant Kuiper Belt. What the two worlds do share is an atmosphere dominated by nitrogen and methane, along with surface chemistry that has been slowly evolving for billions of years in environments completely free of oxygen. The researchers proposed several candidate compounds that could theoretically produce a signal near that wavelength, including certain configurations of hydrocarbon molecules known as allanese, and possibly benzene mixed with some unidentified partner molecule or acetylene or frozen ketene ice. None of these candidates has actually been confirmed. The authors were explicit in stating outright that they cannot yet say what the molecule truly is. NASA's Dragonfly mission, a rotorcraft lander scheduled to reach Titan sometime in the early 2030s, does carry instruments that could eventually help narrow down the possibilities by directly analyzing Titan's surface materials. But that mission remains years away, and even then, it cannot observe this specific spectral feature directly in any case. For now, the unknown molecule remains exactly that, unknown, present on two very different worlds, matching nothing in any existing database, and simply waiting for an explanation nobody yet has. The full story of what Webb has revealed about Pluto across 2025 and 2026 is really a story about what a single instrument can accomplish once it finally has the sensitivity to separate signals that were previously too faint or too tangled to read cleanly. The mechanism behind Charon's polar staining, with Pluto steadily losing roughly 1.3 kilograms of methane per second out into space, and about 2.5% of that material being captured by Charon's gravity and freeze-trapped onto its poles, where radiation slowly converts it into permanent dark organic compounds, had been suspected for years, but could never be confirmed in this kind of detail before Webb arrived. Frozen carbon dioxide and hydrogen peroxide on Charon's surface, confirmed by Webb data back in 2024, had never once been detected there before that observation. The mystery absorption signal on both Pluto and Titan was only visible inside a narrow wavelength window that earlier telescopes simply lacked the sensitivity to probe at all. Pluto, it turns out, has been quietly hiding almost all of its true complexity from every single instrument that came before the one now finally reading it clearly. But to fully appreciate everything Webb is showing us now, it also helps to spend time with what New Horizons revealed back in 2015 and what ongoing analysis of that data has continued turning up in the years since, because the surface of Pluto is strange in ways that reach well beyond its atmosphere. The heart-shaped plane that became the single most iconic image from the New Horizons flyby is formally named Tombaugh Regio, after Clyde Tombaugh, the young astronomer who first discovered the world back in 1930. The pale western lobe of that heart is a massive basin of nitrogen ice named Sputnik Planitia, roughly the size of Texas, filled with ice that is visibly churning in slow, continuous convective cycles. In convection, warmer material rises while cooler material sinks in a repeating pattern of circulation. The same basic process you would see in boiling water or in the slow movement of Earth's own tectonic plates. On Pluto, the heat driving this convection appears to come from the slow radioactive decay of elements buried deep inside its rocky core, far beneath all that ice. The surface ice above it moves in enormous polygonal cells, each one stretching hundreds of miles across, completing a full turnover cycle on timescales of hundreds of thousands of years. A world that was supposed to be completely dead, with no internal heat, no geological activity, just a frozen leftover sitting passively at the edge of the solar system, is in fact still quietly moving. The inside of Pluto has simply not finished cooling down yet. That lingering internal warmth leads directly to one of the most debated hypotheses surrounding Pluto today. Multiple independent lines of evidence point toward the real possibility of a liquid water ocean buried somewhere around 100 miles beneath Pluto's frozen crust, kept from fully freezing by that same slow radioactive heat, driving the convection visible in the nitrogen ice above it. The evidence for this is not a direct detection, it is a pattern. The cracks and ridges crossing Pluto's surface line up in ways that closely match what scientists would expect from a liquid subsurface layer shifting and flexing slowly beneath the crust above it. Sputnik Planitia itself sits directly above what appears to be a positive gravity anomaly, a spot where the underlying mass is noticeably denser than the surrounding ice. On a tidally locked world like Pluto, heavy features naturally rotate over time to face the largest nearby source of gravity. Sputnik Planitia faces directly toward Charon, which is exactly where it would end up if something dense and liquid sat underneath it, gradually causing that section of Pluto's crust to reorient itself over enormous stretches of geological time. The cryovolcanic mountains near Pluto's south pole add another compelling piece to this puzzle. Two enormous isolated peaks rising somewhere between 13,000 and possibly 20,000 feet above the surrounding terrain, with deep depressions at their summits and flanks that closely resemble cooled volcanic flows. If these truly are cryovolcanoes, and the geological evidence strongly suggests they are, then at some point in Pluto's past, a thick slurry of water, ammonia, and other compounds was forced upward from a deep liquid reservoir all the way to the surface. Something warm enough to remain liquid existed inside this supposedly frozen world, and quite possibly still does today. This possibility matters enormously for how scientists think about liquid water across the outer solar system more broadly. Hidden oceans are already confirmed or strongly suspected beneath the icy shells of Jupiter's moon Europa and Saturn's moon Enceladus, both of which display far more dramatic surface evidence of what is happening underneath. Enceladus actively erupts literal geysers of water vapor into space through cracks near its south pole. Europa's surface shows features closely resembling broken Arctic sea ice here on Earth, strongly implying the movement of liquid water beneath its crust. But both of those moons orbit much closer to enormous planets whose powerful gravitational tidal forces generate the heat needed to keep their interiors liquid. Pluto has no large neighboring planet to squeeze it that way. If Pluto really is hiding an ocean of its own, it is being kept liquid by radioactive decay alone, meaning internal heat from radioactivity, a process running to some degree inside every rocky body in the solar system, may be sufficient by itself to sustain liquid water even on a small, frozen world billions of miles from the sun. If that turns out to be true, it fundamentally changes the calculation for how many places in the solar system could potentially host liquid water, pushing that number dramatically upward, since every large, icy object out in the Kuiper Belt suddenly becomes a genuine candidate, and there are hundreds of thousands of those objects still waiting to be studied. The terrain within a region called Tartarus Dorsa adds yet another layer of strangeness to Pluto's already bizarre surface inventory. New Horizons photographed tall rows of jagged blades made of frozen methane, arranged in long parallel ridges, some of them reaching more than 1,500 feet high. Nothing like these formations had ever been photographed anywhere else in the solar system before. Researchers believe they form through a process similar to penitence, ice formations found in high-altitude deserts here on Earth, which typically grow no more than a few feet tall at most. Sunlight causes uneven sublimation across the icy surface, carving out taller sections while lower areas erode away faster, gradually sculpting narrow blade-like ridges over time. On Pluto, that same basic process plays out on a truly enormous scale, using frozen methane instead of water ice, under temperatures and pressures utterly unlike anything found on Earth. A 2025 reanalysis of the original New Horizons data suggested these blade fields may wrap around as much as 60% of Pluto's entire equatorial belt, forming an almost complete ring of jagged frozen terrain circling the whole dwarf planet. Put all of this together, and you get a picture of Pluto that is nearly the exact opposite of what almost everyone assumed before 2015. Not a dead, passive, frozen lump sitting quietly at the edge of the solar system, but a world with genuinely active surface geology, an unprecedented atmospheric cooling mechanism confirmed directly by Webb in 2025, and a slow-running chemical machine producing organic compounds that belong to the same family as prebiotic molecules relevant to the origin of life itself. Add to that an ongoing atmospheric exchange with a companion moon that has been permanently staining Charon's poles for billions of years, an unidentified molecule on its surface that also appears on Titan and matches nothing in the scientific literature as of 2026, and strong geological evidence pointing toward a hidden liquid ocean that could make Pluto one of the most quietly significant worlds in the entire outer solar system. None of this has changed Pluto's formal classification. It remains a dwarf planet under the International Astronomical Union's current definitions, And that particular debate, which occasionally resurfaces whenever a NASA administrator or a prominent scientist publicly calls for the definition to be revisited, is a separate conversation entirely from the underlying science. What the science has actually done is make that label feel increasingly inadequate as a description of what Pluto really is. The classification says small, cold, distant, and unimportant. The data says active, complex, chemically rich, geologically alive, and still generating brand new discoveries as recently as 2026. Webb is scheduled to continue observing Pluto periodically as it rotates back into an optimal viewing position over time. Each new observation adds fresh data points to the picture. The thermal light curves researchers use, which track exactly how Pluto's heat emission changes as the world rotates, are sensitive enough to reveal variations between different terrain types, letting scientists build an increasingly detailed picture of how heat moves across the surface and up into the atmosphere over the course of a full rotation. The mystery absorption signal shared between Pluto and Titan will become a priority target for follow-up investigation, both through additional Webb observations and through laboratory chemistry experiments aimed at synthesizing candidate compounds and testing whether any of them can reproduce a matching spectral signature under Pluto-like conditions. The cryovolcanic mountains will keep being analyzed against the still expanding database of New Horizons data, which scientists continue working through more than a decade after that flyby sent its full data set back to Earth. There is currently no funded mission in development to send a dedicated orbiter or lander to Pluto, largely because the travel time alone, even using gravitational assist maneuvers, runs to a decade or more, and space agencies must weigh that enormous timeline against faster missions closer to home. NASA's Planetary Science Decadal Survey, which sets the agency's exploration priorities for the years ahead, identified a Uranus orbiter and probe as the top recommended flagship mission for the coming decade, meaning the ice giants and Neptune are currently considered a higher near-term scientific priority than the distant Kuiper Belt. That may well change as the true complexity of Pluto and similar Kuiper Belt objects becomes clearer with time, but for now, it remains the current reality. Webb is the only instrument reading Pluto in this kind of detail, and it will remain the only one for the foreseeable future, which makes every single observation Webb sends back from that direction matter even more than it otherwise would if a dedicated mission were already on its way. A world that was formally dismissed in a vote back in 2006, that sat almost entirely unexplored for 85 years after its discovery, that scientists expected to be geologically dead and atmospherically trivial, a world that was supposed to be hiding essentially nothing, has instead turned out to be hiding almost everything. A world that was dismissed, formally demoted, and then largely forgotten by the public is now revealing, instrument by instrument, observation by observation, that it has quietly been doing things no other world in the solar system does, including some things science does not yet even have the vocabulary to fully describe.